First of all, I'm not sure how to pronounce Himalaya. Is it Himalaya, Himalaya, Himalaya? A number of these different versions of the word seem to be commonly used. But hopefully Professor Mike Searle, who's the Professor of Earth Sciences and Senior Research Fellow at Worcester College in Oxford, will be able to put us right on that one. Now, he researches the tectonic, structural, metamorphic, and magmatic evolution of mountain belts, and in particular, obviously, the Himalayan ranges. He retired this year, but continues to undertake active research, mainly in Nepal, Oman, Greece, Cornwall, and of course, that exotic place called Scotland. Tonight, Mike is going to talk to us about the tectonics and mountain building in the Himalayas. Over to you, Mike. Sorry, unmute yourself there.
Thank you very much indeed, Neil. Can everyone hear me now? Yes, good. All right. Well, it's a great pleasure to be with you. It's just a great shame that I can't be up there in Glasgow and give it in person and share a dram or two with you after the talk to reminisce with those of you who've actually been to the Himalayas, call it whatever you like. It's an open world, and the more the merrier. So what I'm going to talk about today is give you a brief run through of the tectonics and mountain building processes in the Himalayas. And the Himalayas is a spectacular, fantastic mountain range. It's about 2,500 kilometers long, probably anything between 100 or 200 kilometers wide, depending on where you take it. And it's ongoing. It's carrying on today as India collides with Asia. And
Mike, do you want to put your screen share back on?
I thought it was on.
It's gone off.
Sorry.
Sorry to interrupt you.
No, that's all right. Is it on now?
No, you've got the wrong, well, you've got a screen, but it's not your presentation.
Oh, okay. Ooh, hang on.
That's it. Just go to the first. I don't know what happened. You must have closed it somehow.
Okay, I had my email on, so I've shut that down. So hopefully that's
up now. Yes. Sorry to interrupt you. Your flow.
Okay, no problem at all.
I've done it myself. I started rattling on and realised I hadn't done it properly. But
yeah, no, this is the problem with Zoom, which is I still don't like at all. And anyway, this is a picture taken by a friend of mine, Leo Dickinson, who's an adventure photographer, who decided to ride a hot air balloon across the summit of Everest many years ago. And they took off very gently from Chawoyu down on the Nepalese side and drifted very, very slowly up to the jet stream. And then the jet stream took them across the summit of Everest at about 100 miles an hour, and they cleared the top by about 30 meters. But he did get some spectacular pictures on the way, hanging out of the balloon with all the oxygen needed to keep the thing afloat. Okay, so the Himalayas, as I said, is the most active mountain range on the planet today. It's responsible, the India-Asia collision, which occurred about 50 million years ago, is responsible for creating the Himalayas and also for the renewed uplift of the Tibetan Plateau, which is by far and away the largest area of high elevation and thick crust anywhere in the world. Everything in white on this picture is above 5,000 meters. The average height of the plateau is about 5,200 meters, pretty much the same as the Himalayas, but the Himalayas have peaks going up to 8,800 meters and deep valleys in between them, whereas Tibet is much flatter topography. So what I'm going to run through is the complete sort of tectonic history of the Himalayas very briefly. So here is a satellite picture courtesy of NASA, and it's taken roughly from the space shuttle, well, exactly from the space shuttle, but roughly over Kathmandu, looking west along the high range of the peaks. Can you see my cursor okay? Good, okay, well, all these snow-capped peaks here, this is all the Himalayas, And we're looking here at central Nepal, going out to the Kaligandaki Valley, and this is the Annapurna range that some of you may have trekked around. This is the Manaslu range. Over here is Ladakh and Zanskar in northwestern India, and right over here is the Karakoram, which spans the borders of Pakistan, Tajikistan, and Tibet. It's an absolutely spectacular photograph. And of course, the space shuttle, it's upside down because that's where it re-enters the Earth's orbit. So we're looking back along the tail fin, upside down, looking along about 2,000 kilometers of the Himalayas and Tibet. So two of the main tectonic discussions nowadays are to do with the lateral extrusion of Tibet. This is called continental extrusion. And the idea is that when India collided with Asia, a lot of the thick crust of Tibet was shunted eastwards out of the way of the Indian indenta, which is what this arrow here is doing. And the thick crust is bounded by these big strike-slip faults. This is the Karakoram fault, and this is the Altintag fault. Both of those are about, the Karakoram fault's about 700 or 800 kilometers long. The Altintag is getting on for 2,000 kilometers long. And these are the faults along which Tibet is supposed to have extruded out of the way of the Indian indenta. The other major tectonic process that we're going to discuss is called channel flow. And this is the idea that a lot of the high peaks of the Himalayas here have been extruded out southwards as a result of crustal thickening, metamorphism, partial melting, and extrusion. And that deep ductile crust is mostly made of high-grade metamorphic rocks, sillimanite-grade migmatites, leucogranite. And the extrusion slab is bounded by these two huge crustal scale faults. One is the main central thrust at the base. This is a thrust fault, very similar to the good old Moyne thrust. The uppermost one is a low-angle normal fault, the South Tibetan detachment. Both of these faults were active during the Miocene. Both of them are seismically dead today. The active plate boundary today is this fault here, the main boundary thrust, and this is the one that a lot of the earthquakes are rattling off, like the Gorkha earthquake of 2015. Okay, so here's a geological map of the Himalayas, very simplified. The main India-Asia collision zone is the Indus Suture zone, called various things in Tibet. And it's this grey zone here, which divides Indian plate to the south from Tibetan plates to the north. The northern boundary is this huge trans-Himalayan batholith, which goes in from Kohistan, Ladakh, along the Gandhisi range. And this is the Andean southernmost margin of Asia during the collision. So it's full of granites, andesitic volcanics, all that kind of stuff. Whereas the Indian place used to be a passive margin, very similar to the Moyne-Dalradian sequence, a lot of high-grade metamorphic rocks. The blue is the upper crust, which is the unmetamorphosed sedimentary sequences. In this sort of browny color is all the high-grade metamorphic rocks, dominantly kyanite and sillimanite-grade gneisses and leucogranite. And in green are the lesser Himalayan rocks, which is a fold thrust belt, mostly of Precambrian and Paleozoic rocks that form the northern margin of India. So when you reconstruct the geology of the Himalayas, it's actually very simple. It's one of the simplest mountain belts on the planet because you can take a transect anywhere from the western Ladakh right over to eastern Nepal and Arunachal Pradesh, and they would all look very, very similar. When you reconstruct the rocks, what we're looking at is a passive continental margin of India. And the Indian place is Archean, the Indian shield, overlain by Proterozoic and overlain by thin Paleozoic rocks until it reaches the Himalaya. And as you approach the continental margin, the Paleozoic rocks and the Mesozoic shelf carbonates get thicker and thicker. And the Mesozoic shelf carbonates are actually very similar to the Tethyan shelf carbonates that we see, for example, in Oman, in the Zagros Mountains and parts of the Northern Alps. So it was a classic Mesozoic Tethyan passive margin sequence that during the late Cretaceous was overthrust by a series of ophiolites, the Spontang ophiolite over here, and a few underlying thrust sheets. So this is the stage around 65 million years ago, when the ophiolites were thrust over the Mesozoic passive margin. So very, very similar to the situation that we see today in Oman, for example. So the rocks present within the Himalaya, you never ever see Archean rocks in the Himalayas. All of the Himalayas are Proterozoic rocks or younger. And the one stratigraphic horizon that is common all the way across these zones of the Himalayas is the Neo-Proterozoic, which is the Hymanta sequence. This is a thick sequence of dominantly black shales and cherts, and you see it forming the sillimanite grade gneisses in the high Himalayas here, and it forms the base of the unmetamorphosed Tethyan shelf carbonate sequence along the margin. So to summarize things tectonically, very schematically, the first effects of the orogenic belt is the abduction of the ophiolites. And there's a spectacular ophiolite up in the Ladakh Himalayas called the Spontang ophiolite, which is old. It's a Jurassic ophiolite. It's not like the Tethyan 95 million year ophiolites we see in Cyprus and Oman, for example. And it has an island arc built on top. The Spong island arc has been dated much younger. So we think actually this is a typical mid-ocean ridge type ophiolite with an island arc, demonstrating the first effects of the subduction zone. Subduction initiation, I think, is probably sometime around 88 when the arc formed above the ophiolite and the whole thing was abducted onto India. The next major abduction is the Dras-Kohistan arc. And over in Pakistan, the Kohistan arc is enormously thick and very, very impressive. And it peters out to the east. So in Ladakh, we have the Dras Island arc, which has the full sequence of Kohistan, but it's much narrower. And then from 50 million years, which is the age of the India-Eurasia collision, enormous amounts of crustal shortening, thickening, high-grade metamorphism at depth. So here is a stratigraphic section through the Kohistan Island arc. And it's one of the most spectacular sections. The whole island arc shows about 60-kilometer crustal section. This is a Japan type island arc, which is the full range from lower crustal granulites and diorites and amphibolites right up to shallower level metamorphic rocks, gabbro-norites, magma chamber rocks up here. And the whole thing is intruded by these trans-Himalayan granites, which are the Cretaceous to Eocene Andean type margin of the south after stitching of the continents and the collision of India and Asia. There are a series of ophiolites along the main mantle thrust at the base, but they're highly deformed and highly altered and highly metamorphosed. But there are gem quality olivines coming from this one here in the Sapat, and a whole series of spectacular garnet granulites and peroxenites, websterites, and that kind of rock at the bottom. So the whole island arc was up-tilted, abducted onto the margin of India, and then the India-Asia collision started in earnest. Well, how do we know the age of the continental collision? It depends really how you define it, because bearing in mind that a lot of the passive margins that we see today, for example, in Oman, the continental crust goes way offshore. So a final date on the final marine sediments in the suture zone is probably the youngest possible age of the India-Asia collision. This picture here is a mountain in southern Tibet, which is absolutely spectacular, because all of these white rocks down here are the uppermost part of the Tethyan Himalayas. And these are shallow marine, foraminiferal rich limestones. They're full of nummulites, acylinas, all of that stuff. It's very, very well dated. And it's dated at P8, planktonic foraminiferal zone 8, which is lower Eocene, 50 million years. These rocks here, the browny, reddy rocks, are all the continental, fluvial, and lacustrine deposits of the continental crust. So the marine to continental transition is right there. That boundary there has fossils in of this age. So there was no more Tethyan Ocean left between India and Asia by that time. And after that, the molasse sequence was deposited, which is the post-collisional basin that formed along the collision zone, along the Indus-Sangpo suture zone. And here's a reconstruction of that basin. So the marine sediments are in blue, and these are the youngest ones, the nummulitic limestones at 50.5 million years. These are all detrital zircon ages from the conglomerates, these things here. And we also have ages from the southern margin of Tibet. So these are the major Khorestan Ladakh type granites, and they are intruded by these younger dikes, which are 47 million years old. So those are truncated at the top of the Indus Basin, or halfway up actually, by these red beds. And after that, everything was continental, uplifted, and sedimentary like this. Right, so the northernmost margin of the Himalayas is beautifully exposed in the Ladakh and Zanskar ranges. And this picture here is taken from one of the high passes of Ladakh, looking across to the Spontang ophiolite, which is up here in the clouds. Sorry about that. These are the nummulitic limestones at the top of the shelf sequence, and the Spontang ophiolites are all these high mountains up here. And the reason that there's very few ophiolites actually exposed in the Himalayas is that they are always form the uppermost thrust sheet, like in Oman, for example. And as they get jacked up during Himalayan mountain building, they're the first things to go, the first things to erode. So you don't see them. But underneath the Spontang ophiolite is this spectacular Mesozoic shelf carbonate section, unmetamorphosed, and it is folded and thrust, showing an enormous amount of crustal shortening and thickening. So in red here are the thrust sheets. This is approximately 2,000 meters of relief in that one cliff section there. And all of these shelf carbonates range basically from Triassic up to middle upper Cretaceous. Another spectacular series of rocks we have on the northern margin of the Himalayas are some eclogites, and there's two main regions where these ultra high pressure eclogites are exposed. One is in northern Pakistan in the Kagan Valley and around. They're very regional there, they're scattered all over the place. And the other one is in the Somarari Dome in the northernmost part of Ladakh. And these are absolutely spectacular rocks. They're garnet ophiolite bearing rocks, so they're ultra high pressure eclogites because they have coesite in. Coesite is the high pressure polymorph of quartz. And some of them even have microdiamonds in, which means they're getting up to 30 kilobars plus. So that's 150, 200 kilometers depth of burial. This is the boulder, the famous boulder that was first discovered by Paddy O'Brien years ago. And this is the one that has been dated. So a lot of geochronology has been done on these rocks, and this is a summary diagram of the uranium-lead ages. Alanites and zircons record the peak ultra-high pressure metamorphism, 46 to 40, almost plumb on 46, and titanites and rutile are slightly lower temperature. They're not nothing like as low temperature as argon muscovite ages, for example. But what these ages do show, these all came from one sample. What these ages do show is that peak ultra high pressure metamorphism was about 47, 46 million years. And as soon as they reached their maximum depth in the subduction zone, you had some sort of slab break off, and then the things popped straight back up the subduction zone the way they came down. And to go from depths of over 100 kilometers here up to the base of the crust in less than 1 million years. So that's an incredibly rapid exhumation rate through the mantle. When it hit the base of the crust, it was then entrained in the normal Himalayan kyanite sillimanite grade rocks, and it showed a more reasonable PT path there. This is what the rocks look like. Everywhere E is an eclogite locality. This is the Somarari Dome. Here's the suture zone. So these rocks were the leading edge of the Indian place as it went down the subduction zone. And they are basically basaltic rocks. These were Panjal trap type volcanics intruded into the Mesozoic shelf carbonate sequence. And that's what happens when you take a basalt or a carbonate down to 150 kilometers and metamorphose it. So here's the PT path going from the depths of anything up to 38 kilobars pressure very rapid exhumation down up it through the mantle. And when it hits the base of the crust, you've had normal clockwise related PT kyanite paths. Now the ages of that, you'll notice, are just slightly younger than the age of the youngest sediments in the suture zone. So the big question is, are they related to the final stage of the aphyolite abduction, like we see in Oman, for example, the Sefer eclogite, or are they related to the first effects of the continental collision? And the jury's open. One probably almost certainly leads straight on to the other. So what happens in the shelf carbonates of the Zanskar? This is the northernmost margin of India. So we're looking here on some mountains to the west of the Zanskar Gorge, which is a spectacular gorge that cuts right the way through the mountains. And we're looking probably at about 3,000 meters of relief from the bottom of the Zanskar Gorge up to these peaks up here. And I've just superimposed here, yellow lines are just tracing around bedding, around folds, and the red lines are thrusts, detachments. So this is how you thicken the crust. We know that the Himalayan crust is thick today. It has been since 45 million years at least. And this is exactly how you thicken the crust. These limestones were all part of the standard Mesozoic shelf that we see all the way along the Zagros Mountains, Oman, and all the way around the Tethyan Himalayas. As you get deeper in the crust, the deformation becomes a little bit more ductile. And this is what happens at the base of the Zanskar shelf carbonate sequence. Again, the red lines are detachments, thrusts, and the yellow lines are just tracing around bedding. So I've spent quite a long time in the Zanskar region, and it was the first trip I did to the Himalayas in 1982. And I've subsequently spent about 10 field seasons in Zanskar. And most of the Zanskar River was this gorge that cuts this gorge through the mountains right in the middle. And it was always a big problem because you couldn't get in there in summer. The gorge was too steep. There's no trekking paths. There's no villages anywhere. But the river does freeze. So we did a winter trip there in 1995, I believe, where we walked on the frozen river from Leh in the north down to Padam in the south, and then skinny skied out towards Kashmir in the west. Absolutely fantastic trip. And this river was just sheet ice. Well, on the margins was sheet ice and big icebergs floating around. And we went with 4 Zanskaris from the gorge, from the Padam region, who knew the gorge very well. And it was just a fabulous trip. Since when they built a road halfway up the Zanskar Gorge, which is kind of cheating because you can just drive up in a Jeep, look across the river and see all these spectacular fold structures. And the deformation, the geology of the Zanskar River is absolutely amazing. I mean, it's incredibly complicated. And a lot of it involves vertical mapping, horizontal mapping, vertical mapping, cross-section construction. And again, this just outlines some of the complexity of the deformation in the northernmost part of the Himalayas. And the yellow lines, again, are just tracing bedding. This is all in Jurassic and Cretaceous carbonates of the shelf carbonate sequence. And the red lines are detachments. Here's another example, beautiful folds, incredibly tight synclines, anticlines. You can work out, well, with a huge amount of problems, you can determine the minimum amounts of crustal shortening by unwinding those folds and thrusts. So this is the Zanskar River, and the new road now goes from Padam about a third of the way up the gorge and then just stops. In winter, this river is frozen, and it was here that we were able to actually put on skis and ski into Padam. An absolutely fabulous trip. Beautiful blue skies every day. The mountains were just completely snow covered. And these villages where they just literally hibernate for about 5 months during winter, they welcomed us with open arms and glasses of Chang, and absolutely wonderful people. The Ladakis are fantastic people. Okay, so what happens from the India-Eurasia collision at 50 million years is that the upper crust folds and thrusts like the pictures I've just shown you. The same happens in the deeper middle crust and lower crust, but there, of course, the pressures are high enough to become metamorphic rocks. So we've seen that the peak eclogite metamorphism occurred about 47 million years. After that, the major collision of India and Asia. And then there was a prograde metamorphism, which was a standard Barrovian metamorphic sequence, just like the Highlands of Scotland, storolite kyanite grade metamorphism. The peak pressures we get, about 10, 12 kilobars in the kyanite zone, are dated using uranium lead monazite at around 35 to 30. And then you have a decompression to sillimanite grade metamorphism, sillimanite cave feldspar plus melting in the migmatites. And that partial melting results in formation of the leucogranites. And then you have a period of very rapid exhumation, followed by a relatively steady state exhumation. And then what we see today in the landscape is the last 2 million years of glaciation. So here's a summary diagram of what's happening. So this is what I call the Oman stage. This is where the ophiolites were abducted onto the passive shelf margin, just like we see in Oman. And the collision of India and Asia occurred on the Indus Suture zone, with the final marine sediments at about 50 million years. And then after that, big crustal thickening. And then the eclogites, which were TM is Somerari. And these are where the basaltic Panjal dikes and sills were intruded into the shelf carbonates. And these rocks were taken down to these depths at about 47 million years old. And then they were exhumed very rapidly up to the base of the crust, where they became entrained in all this kyanite sillimanite grade metamorphic sequence here. And by this time, the plates had collided. We're up into continental sedimentation along the suture zone, no trace of any marine sedimentation after that. And the final phase is a decompression from kyanite to sillimanite grade metamorphism, where the pressures are slightly less, temperatures are slightly higher, and you cross the Muscovite melting curves. So as soon as you do that, the rheology of the middle crust goes completely, and it starts extruding out to the south, bounded by this low angle normal fault along the top and the main central thrust at the bottom. So we've known about these low angle normal faults for 30, 40 years. And of course, the geophysicists don't like normal faults, because we never see, or we hardly, very rarely see any earthquakes on them today. And they say you've got to have a fault at a steeper angle in order to get an earthquake, like we see, for example, in Greece and all over Tibet today. But actually what we've seen in the Himalayas, this was a model that we proposed way back in 1989 with the folded isograds to explain the inverted metamorphism along the base and the right way up metamorphism along the top, and this big thick central zone of mid-crustal rocks extruding out to the south, bounded by a thrust at the base and a normal fault at the top. And this is all in the kyanite grade rocks in Zanskar. These are the kyanite grade peelites, and these are the marbles that are folded in these spectacular recumbent folds. So this is another profile through the Dhaulagiri Massif, taken from the, this picture is actually taken from Poon Hill, which some of you may have trekked up towards Annapurna. And this is the spectacular view looking across the Kaligandaki Gorge to the peak of Dhaulagiri, which is one of the 8,000 meter peaks. In fact, Dhaulagiri and Annapurna are the only two 8,000 meter peaks which are actually in the Tethyan Himalayan zone rather than the GHS. Most of them are up in the top of the GHS. But what you see here from the main central thrust zone, way down in this region here, is an inverted metamorphic sequence, biotite, garnet, kyanite, sillimanite. As you trek up northwards through the Himalayas, the metamorphism gets deeper and deeper with time and space. So this is a pretty unusual situation. The South Tibet detachment here was first mapped out back in the 80s, and it is absolutely undoubtedly present. It's there. It was active at low angle right the way through the Cenozoic, and it was active at the same time as the main central thrust. And all of these rocks up in this region here show partial melt textures. So we actually have the earliest melting in kyanite grade rocks, and then the later melting in sillimanite grade rocks down here. And it's all of this partial melting that triggers channel flow. And this is what a lot of the Himalayas is made of, this beautiful sillimanite, muscovite grade migmatite, which are in situ partial melts that generates these massive great leucogranite dikes and vein networks across the Himalayas. So here's a picture of Dhaulagiri. This one is actually taken out of a plane when we were doing some filming for the History Channel, of all things. There's 3 rock types here, the kyanite gneisses. These are clinoperoxene tremolite cave feldspar marbles, granulite facies marbles, and these are unmetamorphosed sedimentary rocks. And they are bounded by the Annapurna detachments, which are these low angle normal faults. So those 3 rocks have pressures that you can constrain to these depths here. The deepest kyanite grade gneiss is about 40 kilometers, and the calcsilicate's up here. And you've got to bring all 3 of those rocks to juxtapose next to each other, which is what you see today. And that's where the whole story of these low angle detachments comes in. The hanging wall remains stationary. It's the footwall that moves up. So you're moving these rocks up from here all the way up to here during collision. Okay, Everest. Everyone is fixated on Everest, including me. It's a fabulous mountain, and it's on the border of Nepal and Tibet, and this is in the part of the Himalayas that is absolutely spectacularly well exposed. So this picture here is again taken by Leo Dickinson out of his hot air balloon just before he crash landed in the middle of Tibet. And it shows the Kangshung face of Everest. This is the east face of Everest. Choyu is another 8,000 meter peak to the west, and then Shishapangma over here. And there's all of these peaks that you see in Nepal if you trek up to Everest Base Camp here. The early Himalaya UK expeditions, Eric Shipton and all of his crowd went up this way from the Rongbuk Glacier up through the North Col, and they were attempting the North Ridge route up through here. So this is a map I produced of the Himalayas. This is a result of 6 field seasons, 4 to the Nepalese side, 2 of them to the Rongbuk Glacier and Tibetan side, and 1 to the Kangshung face on the east side in Tibet. And cross sections from there show this South Tibet detachment normal fault absolutely spectacularly. Here's the normal fault, and it divides unmetamorphosed Ordovician limestones at the top. Through the Everest series rocks, everything below here is metamorphic. These are the calcsilicates of the yellow band. These are the staurolite kyanite grade rocks of the Everest series, and these are the big leucogranite sheets. Now, they don't look anything like leucogranite intrusions that I was taught when I was an undergraduate. These are horizontal layered sill complexes emanating out of a huge mid-crustal migmatite zone. And when they were extruded to the freestanding south, they formed these great ballooning sill complexes like at Nuptse. So it may seem strange that the highest mountain in the world, Everest, is cut by 2 normal faults. Normally you expect normal faults in places like the North Sea or the East African Rift or some basin and range. How on earth do you get normal faults in a compressional mountain range? And this is one of the big things that's resulted from all the Himalayan work from several people. During the mapping, when I was mapping the Everest Massif, I was hugely helped by Bradford Washburn, who's died now, but he ran the National Geographic topographic map. And during the making of the National Geographic map, they flew a Learjet across the Everest Massif and photographed it in ultra detail. And he was good enough to give me a lot of the aerial photographs of Everest, and I used those for some of my mapping. This picture here is looking straight down on the summit of Everest, 8,850 meters. This is the southwest face where Doug Scott and Dougal Haston did the first ascent. And this is the Kangshung face over here where Steve Venables did one of the early oxygenless ascents. Well, obviously he breathed oxygen, but bottled oxygen. And then I was also helped enormously by 3 climbing friends of mine who, Everest is their office. They troop up and down every year, or at least they did before COVID. One of them is Kenton Cool, who's a geologist, undergraduate, became a professional mountaineer, and he guides people up, high-spending clients up to the summit of Everest every year. So I persuaded him to collect me a load of samples from the top, which he did. And in some of those samples, we have spectacular crinoid ossicles. And there's even bits of trilobite, nothing like this sample here, but there's fragments of trilobites, fragments of crinoids in the muddy limestones from the summit of Everest. So these rocks here are where they collected the samples from. And there is a spectacular horizon here of thrombolite, which is now called matte limestone band. And then you hit the Chomolungma detachment, which is the uppermost one of the South Tibet detachment normal faults. The yellow band is made of calcsilicates and marbles, high metamorphic grade. And then you're into the greater Himalayan metamorphic series to the south. So here are two thin sections. This is a rock sample collected by the great Ed Hillary himself on Summit Day, 29th of May, 1953. And this is undoubtedly a sedimentary rock. This is a limestone in which these crinoid ossicles have been found in other samples. This rock here was collected by Charles Evans on the first attempt, which was 3 days before Hillary and Tenzing. And this is collected from the yellow band. And this is undoubtedly a metamorphic rock. These are both now in the Cambridge Harker collection. So further down the Rongbuk Valley, which is an absolutely amazing place to go, you have to drive for days across the Tibetan Plateau, and then you come in from the north and you follow this great glacier to it, valley to its head, and it leads all the way up to the North Col eventually. And this is the route that all the early Everest expeditions took. So we had 2 PhD students in particular to do a lot of the mapping and the pressure temperature work along transects in the Nepal side and the Tibetan side. And these were Micah Jessup and John Cothell. And we had a whole series of papers produced from the results of the mapping combined with the thermobarometric data and a lot of uranium lead data as well. This is a picture of the lowermost Rongbuk Valley. And if people, these geophysical friends of mine who say low angle normal faults don't exist, well, here is one. And it's putting unmetamorphosed Ordovician limestones against amphibolite facies metamorphic rocks and Luca granites. So that's a very sharp boundary. It's got high strain rocks along it, and it's got a big PT jump across it. We've done a lot of work dating all the different Luca granites in the footwall to constrain the ages. So this is a picture of Rick Law, who's my co-PI on several NSF grants to enable us to get all this work done. And you can see that the early Luca granite dikes are parallel to the metamorphic schistosity. And there's a few late dikes that cross-cut the early ductile fabrics. These dikes are themselves truncated at the brittle STD contact at the top. So these have all been dated, and we can now constrain the age of ductile deformation, the age of Luca granite, and the age of brittle deformation. And this is a summary of all of those ages here. I'm going to rush through because I'm running a little bit short of time. Cross-section of the entire Everest Massif from the Nepal side here and the Tibetan side. There's the top of Everest with its Ordovician limestones. There's the Chomolungma detachment. And you can actually physically walk and touch this detachment for 70 kilometers across strike, from the summit of Everest, just below the summit of Everest, all the way down here, clipping these high peaks before they merge with the Luca granite detachment here and dive off underneath the Tibetan Plateau. So there is absolutely no doubt at all that the minimum amounts of offset on that normal fault are 100 kilometers. When you've taken into account the pressures along the footwall rocks, it's more like 200 kilometers. And this is an active low angle normal fault in a compressional environment during the Miocene. So we've now got a huge amount of data on pressures, temperatures, with distance and strain deformation here. And there's a summary. India-Asia collision at 50, crustal thickening, peak kyanite grade metamorphism at 32, decompressing to sillimanite muscovite, which produces migmatites, crustal melt, leucogranites. And this is the time of channel flow. And then channel flow ends at about 16 when the brittle faulting takes over. And after that, it freezes up. So a few pictures. This is from another climbing friend of mine, Marco Przelt, who's climbed Gaichung Kang. And these are the two this is just west of Everest. And it's just below 8,000 meters, which means nobody goes there. Marco did, I think, the 13th ascent of this mountain, whereas thousands of people have climbed Everest. But it does show two spectacular low-angle normal faults. There's the Chomolungma detachment, and there's the one at the top of the Nuptse Everest granites. And that is a fault. It's not an intrusive contact. So you can take the pressures and temperatures from the metamorphic rocks around Everest, convert the pressures to depths, assuming pressure gradients of normal, which is perfectly valid. And we get, and you also assume that the same dip of the South Tibet detachment was there since the Miocene, which is also perfectly valid. And these rocks here were formed at these pressures at these depths, 15, 20 kilometers underneath the Tibetan Plateau, approximately 100 kilometers north of the summit of Everest today. And they were brought up from here to juxtapose rocks together that we see at Everest Base Camp. It's just like the Annapurna Dhaulagiri section I showed a bit earlier. The granite story is incredibly interesting. They're all 100% S-type granites, 100% crustal melt granites. Most of them are formed by muscovite dehydration reactions at relatively low temperatures and relatively low pressures. They are spectacular because they are full of tourmaline, garnet, muscovite, biotite, cordierite, even andalusite as a magmatic phase. The second reaction is the biotite dehydration reaction in pilitic rocks, which occurs at slightly higher temperatures. And at these temperatures, cordierite is the stable phase at low pressure, garnet is the stable phase above about 5 kilobars. And these are the spectacular cordierites that are formed at the late stage within some of the leucogranites there. Another picture taken from Shishapangma, tried to climb Shishapangma, got very close to the summit. This picture here was taken at about 7,200 meters, looking straight down on Tibet, and we're looking straight down the South Tibetan detachment. These are the black shales of the Cambrian Ordovician sediments. These are the leucogranites, which are dated at 20 to 17 million years. And the plateau, here's the nice flat southern Tibetan plateau at about 5,200 meters. So this is a map showing the structure contours on the South Tibetan detachment from the summit of Everest here all the way down the Rongbuk Glacier. And this diagram on the right shows all of the geochronology. We've now got a huge amount of geochronology on the Everest Massif, and you can see that the metamorphic ages are all, prograde growth ages are all in green, and the underformed leucogranites, the cross-cutting leucogranites are all in brown. And by 15 million years, all the metamorphism and the granite formation was over. Strain had been, it was frozen in, jacked up, and all the strain was down on the main boundary thrust and the lesser Himalayas to the south. So this is the model of channel flow that we proposed in 2006, and I'm pretty convinced that it still works to this day. Everything on the Indian plate is constrained by geological mapping in the Himalayas, where everything's dipping off to the north. Tibet's pretty flat, and you can't see any of the lower crust. So all of this is constrained by deep geophysics, particularly the in-depth and the high climb experiments, where they imaged the Moho. They imaged this incredible mid-crustal zone of partial melting, which traces exactly, once you've unwound all these later faults and thrusts, to the mid-crustal section we see in the Himalayas. And the granites at the top of Everest are here, 17 million-year-old granites. And these little blobs here, which the geophysics people call partial bright spots, are actually partial melts. And they, I believe, they are leucogranites forming right at this day, present day, about 20 kilometers depth underneath the southern Lhasa block. How do we know what the lower crust is? Well, that's interesting because, I'll show you in a little bit why that's interesting. This picture here is taken from the Kangshan Valley on the northeast side of Tibet, and we're right in the middle of the channel here. And this is almost like a conglomerate. It's absolutely incredible. That's Micah Jessup standing there for scale. And these are huge boulders of selimonite biotite gneiss with older leucogranite veins in them. And they are swimming in a sea of this 17 to 20 million year old granite of the Everest Nuptse granite. So we're right slap in the middle of the channel here. The top of the channel is exposed up in the advanced base camp up on the top, right at the head of the Rongbuk Glacier on the north side. This is Russell Bryce's base camp. We camped on the side and snuck in here for a coffee and a chat and a couple of emails in the internet tent up here. But this is the cliff section right above what used to be Camp 3 in the old 1930s expeditions. And this dashed red line indicates the upper level of the leucogranite. And then the Everest series up here is showing more right way up metamorphism in the staurolite grade rocks to the south. Well, on the Nepalese side to the south, there's another bunch of spectacular mountains all around Everest, the satellite peaks of Everest. And one of them is Amadablan. And this is the projection of the South Tibetan detachment, Chomolungma detachment, as you see on Nuptse, which is just off to the left, and the Everest Horseshoe region. And Amadablan has an absolutely spectacular cliff section here. That's probably two kilometers from bottom to top, 2.5 kilometers maybe. And these rocks here are all the leucogranites. These are the 20 to 17 million year old leucogranites belonging to the base of Everest and Nuptse. And you can see these dikes, which are feeding the next sill complex above, and they're all being bent around to the north on the footwall of the South Tibet detachment. And the Chomolungma detachment, remember, puts sedimentary rocks above high-grade metamorphic rocks. So age dates of these rocks constrain the maximum age of shearing on the South Tibet detachment. Another really interesting factor is on the fabrics. When you trek up the Himalayas, if you trek up from Lukla up to Everest Base Camp, all you see are these thrust-related shearing fabrics all the way up to about midway. And when you pass the selimonite K felspar melt Isograd, which is the first of the big migmatites, then the fabrics suddenly indicate top to the north. Well, these have all been mystery to people because they say, how can you go from compression to extension? You don't need to. The Himalayas has been in compression ever since 50 million years, still is today. All it means is that you're bringing these rocks up in the footwall of the South Tibetan detachment while the hanging wall stays where it is. And that's what a low angle normal fault does. Not only here, but we're finding them now all over the place. The Aegean is full of them. Naxos, Paros, core complexes are full of them. They're all over the place. And I think the Basin Range is the place that somebody needs to go and have a real hard, good look around to see if these things really are whole crustal lithospheric extension or whether they're Himalayan type low angle normal faults in some sort of compressional environment. So anyway, the Himalayan channel flow model is alive and kicking and well, and all the data fits this model, along with the South Tibet detachment low angle normal faults on top. And it's really this mid-crustal channel of dominantly migmatites and leucogranites extruding out to the south above the main central thrust and below the South Tibetan detachment. How do we know what these rocks here are in the base of the Himalayan crust? These are high pressure granulite, and we know them because in southern Tibet, there's a whole series of these spectacular lampropheric dikes. This is a Shoshanite dike, 12 million years old, 12.7 dated, and it has a whole bunch of crustal xenoliths in them, tiny little xenoliths, no bigger than that. And these are dominantly granulites. There's a whole series of incredibly interesting rocks, mafic, ultra high temperature, high pressure granulites, temperatures way up 1200 degrees centigrade, 25 kilobars. There's restitic ultramafic rocks, hornblende biotite, and there's felsic granulites. So these indicate very thick crust by this time. And then the in situ ages we've got from those tiny xenoliths using zircon and monazite are all the same. So one final part of the story of the GHS is that in the far west, there is what we call the Nanga Parbat Syntexis, the western Syntexis, where the whole Himalayan belt, which is 2,500 kilometers long, goes around the bend and starts going north-south along the western margin of the indenting Indian plate. And this has been mapped since the days of D.N. Wadia, the great Indian geologist who worked in this region in the 60s and 70s. And he thought all these rocks were Precambrian. High-grade metamorphic rocks must be Precambrian. They're full of sillimanite, garnet gneisses, high-temperature cordierite, K-feldspar, sillimanite, garnet, tourmaline. A lot of the cordierite coronas indicate melting at very high temperatures. I collected a load of samples along the Rykop Valley up here, up to midway up the Rykop face up here, which is as far as you could go. The upper parts of Nanga Parbat are absolutely extreme in terms of steepness, climbing ability, dangerous as hell. And the upper samples I've got are from these outcrops right here. And we've dated uranium, lead, monazite, and xenotime ages as young as 0.7 million years old. That's quaternary high-grade metamorphism, partial melting, and granite formation. These are the youngest granites anywhere in the world, and they are right in the core of the Nanga Parbat core complex up here. Really interesting. They might even be representative of what is actively going on metamorphically at the deepest levels of the Himalayas underneath southern Tibet right now, today. So these big green things here are big cordierites, and these are cordierite garnet veins. These are the partial melts which intrude, and the youngest dates we've got are from these things here, these tourmaline-bearing leucogranite partial melts, 0.7 million years old. Those are enormously high exhumation rates. And I think what is happening is it's being buttressed by the Kohstan arc on the west, and its channel flow, which hits the buttress and goes vertically up, like a kind of mid-crustal fountain. So Nanga Parbat is incredibly interesting. This face here is 6 kilometers from top to the Indus Valley, which is off the picture down the bottom. And it's been through the entire Himalayan cycle. All of this is exactly what we see on the main Himalayas. The ages get progressively younger in some of the North Himalayan domes, but Nanga Parbat also shows this very young Pliocene quaternary metamorphism, high temperature metamorphism, partial melting, and granite formation. It's an incredibly interesting place. And I think the story is, it is a core complex. It's bounded by these two major faults, thrust at the base, Liachow thrust, and the normal vertical stack fault here. It's connected at depth to the Zanskar Himalayas, which are over here. And this is what I mean by a kind of vertical channel flow. What happens on the other side of Tibet? Well, that's another hour-long lecture, which we'll have to wait for another time. But two very simple diagrams here. This one is in the central part of the Himalayas, central Tibet, the Gangdesi granites we've had a brief look at along the southern margin. Very flat plateau, very high, and there's a whole series of suture zones across the plateau as you go to the north. What is jacking the Himalayas up is probably the ecligatized granulites of the Indian Shield. So these are if you have a granulite in the Precambrian, an Archean granulite, you take it down to 100 kilometers, it's not going to do much. It remains a very strong, very dry granulite facies rock. But I think the granulites and the ecligites down here at the base are the strong lower crust that keeps the Himalayas actively high. Another profile, this is in the west now, so this is across the Zanskar Ladakh Himalayas here, the main boundary thrust over here, and this is the Zanskar range with all those spectacular folds and thrusts. The Asian plate here is in the Karakoram is all incredibly high-grade metamorphic rocks, everything in grey, is kyanite, sillimanite grade or younger, with an enormous granite batholith that forms the Trango Towers and all of those spectacular rocks. K2 is up here. And all of these are again Cenozoic. So you have a massive history of crustal melting, high-grade metamorphism, and crustal melting on the Asian plate exposed in the Karakoram. This is one of the great frontiers. It's so difficult to work there. I've had 8 expeditions to the Karakoram, and each one lasted 2 to 3 months. It took us 14 days to trek to the base of K2 from the end of the road. So you need a month just to get in and out. And you need a whole string of porters. It's like organizing an army. But the geology is absolutely stunning. Anyway, that's for another day. Tibet, as I've said, we rely pretty much on seismic experiments to figure out what's going on at the base of the crust. And all of them, going back to the 90s experiments of Owens and Zant, and the youngest one, which is the in-depth profile, shows that the southernmost part of Tibet is underlain by cold mantle, whereas the northern part of Tibet is relatively hot mantle. And this is where the active volcanics and the lamprifiers and the Shoshonites are intruding today. So one other story is, I'm sure you've all heard about the Gorkha earthquake, 25th of April, 2015. I was due to go to Nepal a week after this earthquake, and it was a complete disaster. It was a very big earthquake, relatively 7.8. The depth was about 15 kilometers, and it ruptured about 100 kilometers of the main boundary thrust here, jacking this up. This is the Kathmandu Valley. The mountains to the north of Kathmandu rose by about 1 meter, 1.1 meter in about 5 seconds. The whole Himalayas tilted to the north. So actually Everest, which is up here, actually went down by a few millimeters, soon to be rebounded. The big problem was that in this earthquake, there was no surface rupture. What should have happened is the earthquake should have triggered about here, and it should have broken up one of these thrust faults along the base down here in the Siwaliks, but it didn't. There was no offsets at all, which means that the rocks here, the fault ruptured about 4 to 5 meters horizontally underneath Kathmandu, and that strain is all still down there. It's yet to come up. So another earthquake is going to happen very soon. We don't know when, but it will definitely happen. And when it happens, the rocks that will be affected are these rocks here. This will rupture to the south, or the area from Gorkha to the west, which did not rupture at all. So Pokhara was almost unaffected by it. Kathmandu was really badly affected by it. And the worst effects of the Himalayan earthquake in Gorkha were actually up in the mountain villages, where some villages were just completely flattened. The Langtang Valley collapsed. The whole of the south face of Langtang Lirung, which was the first Himalayan route we did, that route has now totally disappeared, and the entire mountain of Langtang Lirung collapsed, buried the entire Langtang village, killing everyone. Total disaster. So it's really important to figure out what's going on in Himalayan earthquakes.
So I'm going to try.
So just,
No.
Can I just finish off very quickly with a comparison of Scotland? So I've been working in Scotland, taking students up to the Moyne Thrust for years, and I've been really enjoying sort of reconstructing the Caledonian collision in Scotland with the Himalayas. And I've got a paper coming out in the Geological magazine with all this story. And I think there are huge comparisons to be made between the Caledonian mountain orogeny in Scotland and the Himalayas, including in the metamorphic story and in the strike-slip faults and in the back-thrusting zone, which occurs along the Highland boundary fault here. Okay, so that's all I'm going to say. I will just make a quick plug before I go for my book. If you like stories of geological expeditions to the Himalayas, it's all in my book. Paperback edition is now out at £19, which is an absolute bargain. It's less than a round of beer in the pub. And there's 40 years of work that's gone into that, 30 years of work. Also a big plug for our conference next week in the JOLSOC London. This is on celebrating the work of William Smith and geological mapping. And we've made 3 videos, including Owen Green has made this one on the origins of geological mapping and William Smith. I made one on the Highland controversy, the whole story of Peach and Horn and Lapworth and the discovery of the Moyne Thrust, and another one on the mapping the Himalayas from the Great Trigonometrical Survey of India to my Everest map of 2007. So if you can, I recommend you join our conference, buy my book, and hopefully I will see you in person next time I'm up in Glasgow. Thank you very much. And apologies for running over time a little bit.
I don't think you were over time at all.
Okay.
Thank you very much for that, Mike. Can I ask a quick question here? How are people going to be able to get hold of your book then? All good bookstores.
All good bookshops, correct. Or online through the Oxford University Press, or easiest way, like everything, is Amazon.
Yes, of course. No, that's good, because I'm sure there'll be a lot of interest in that.
Sure. Now, if I was up there, I could have bought half a box full, but unfortunately, COVID has delayed that.
Yeah, I bought mine off Amazon, so it was,
oh, great.
It was very simple. I just wanted Mike to come so he could sign it for me. But
yeah, there it is. This is Layla Peak in the Karakoram, which is the most beautiful mountain on the planet. And yeah.
We've been asking for a link to the GSL conference. Is that something you can do, David? Add that to the chat.
I've got it. I can do that and email it out to everybody along with a link to the video of the recording of the talk, and that will obviously have the link. And I'll send an email out with all the links that's needed for this. I'll do that over the weekend.
Okay, that's great. I presume that you're happy to answer any questions.
Yes, absolutely.
We do have a few questions on chat. Is John Eiley able to unmute himself?
Yeah, so I've unmuted myself now.
Ah, good.
You hear me okay?
Yes, would you like to ask your question then?
Yeah, I've actually put the question in the chat. Basically, it's about the tectonics. Given the compressional tectonics we were talking about, how does this affect the height of Everest? Is Everest actually still rising in altitude?
Yes, we've had GPS stations from just below the summit of Everest now for 25 plus years, and it's still rising. It's going up. So there is nothing collapsing. Those normal faults are nothing whatever to do with orogenic collapse. Tibet is still rising. Himalayas are still rising. India is still moving north relative to stable Mongolia. It's an active system and it's still ongoing.
So is this being driven by the compressional tectonics in general?
Yes, I mean the whole thing is driven by spreading centers in the Indian Ocean that are pushing India to the north. And as soon as the spreading centers stop, then erosion will take over and wipe the Himalayas back down to sea level, which would be an absolute tragedy.
Thanks for that. Thank you.
We have another question from Roger and Helen Dunshee. Would you like to ask the question yourself, or would you like me to ask it for you?
No, I'm happy to
Oh,
ask.
there you are, Roger. There you are.
Hi. This may be an impossible thing to answer, but in terms of the pace of these things, in terms of the orogeny, is there any evidence as to whether it may be slowing down or speeding up, or when it might finish? Is there any sort of clever ways of finding that sort of thing out? Thank you.
No, I think you're right. They're all impossible. The GPS is extremely good, but it's not in the realms of is India slowing down. We know what the present day north-south convergence rates are. We know what the uplift rates of the central Nepalese Himalayas are. And we know where all the seismicity is going off. So we know where to expect the next earthquakes. What we don't know is when those earthquakes will go off. We know where they're likely to go off, but never when.
Okay, thank you.
Is there anybody else with? Oh, yeah, I see Maggie's got her hand up. Would you like to ask a question, Maggie? You'll need to unmute yourself first.
That was an absolutely marvellous talk. Thanks very much. I was kind of under the impression that the Chinese earthquakes were a result of the Tibetan plateau or the Himalaya whole thing sliding down to the east. Is that right?
Well, you're quite right. The Tibetan earthquakes are very different from the Himalayan ones. The Himalayan ones are all the same. The Himalayan ones are all thrustful earthquakes related to the building of the Himalaya.
Yeah.
But in China and Tibet, there are earthquakes mostly along big strike-slip faults. So all of the big earthquakes that have been known about for the last 30 years have been on massive great strike-slip faults related to the possible eastwards extrusion of Tibet.
Yes, yes, that's what I wanted. So, but it doesn't imply that the Himalaya are going down anymore.
No, not at all. The Himalayas are still rising. Tibet is still rising.
But it's the extrusion of the...
That's right.
Okay.
The extrusion of Tibet eastwards is a big topic of debate because it's actually not extruding. The eastern margin of Tibet on the Longmen Shan is absolutely nothing like the Himalayas at all. It's actually Precambrian rocks exposed above, right along the eastern margin of Tibet. So it's just being passively uplifted on these big steep faults.
Yeah. And
some of them, the Shanshui-He fault has had 3 magnitude 8 earthquakes in the last 150 years. And they've absolutely destroyed whole towns.
Right.
But they're generally strike-slip movement.
Right. Thanks.
Pleasure.
I realize that it's very difficult for some people to write on the chat to ask any questions. If anybody has any questions now, would you like to unmute yourself and maybe ask a question?
Could I ask a question?
Yes, of course. On you go.
Thank you very much. Mike, you mentioned the slab break, and when that happens, you get uplift, and that tends to terminate the deposition within the Indus Basin. Some people have suggested that the slab break-off occurred at different times from east to west along the Indus-Sangpo suture zone. From something like 25, 26 million years ago through to about 17 million years ago, so that the fill of the Indus Basin gets younger as you go east. Do you think the evidence for that is sound, or is it within sort of error limits of dating?
Well, there's 2 different things, Danny. One is the slab break-off is related to exhumation of the eclogites. So you take eclogites down by dragging bits of thin continental crust down into the mantle to get the ultra-high pressures. To get them up, you must have some sort of slab break-off. Otherwise, the mantle, the root, would pull it down into the mantle, and it would either disappear or end up within the mantle convection system. So you need slab break-off to get the UHP rocks back up to the surface. What you're talking about is not slab break-off. That's in the high-grade metamorphism. And the range of ages younging to the east is purely a reflection of the leucogranite uranium-lead ages. And I suspect the data is actually not good enough or wide enough to say that's true, given that parts of the Indian Himalayas are very poorly dated, and parts of like Bhutan are very well dated. So it could be just a dating problem that we haven't got enough ages from the west or the central part, but it's out there.
Okay, thanks.
Thank you very much for that. Also, thank you very much for Stuart Redwood, who's saying what a great talk, Mike, from Panama City.
Oh, wow.
Great.
Fantastic.
Also,
amazing.
And Adrian Burrows, you were wanting to ask a question. Is Adrian there to ask it, or would you want? Quite happy to ask it for you. What is driving India north, he's asking.
Well, that's the spreading centers in the Indian Ocean. So you know, India is attached to all the oceanic plates to the southwest and southeast. And there's a spreading, the Indian Ocean's quite complicated. There's 3 spreading centers. One comes out of the Red Sea and they all meet at a triple junction. But the Indian plate is actually a contiguous plate that's being pushed to the north by the central Indian Ocean basin. So that's what's ultimately driving it.
Okay, thank you. Peter Trelaw, you can make a comment if you wish.
Yeah, hi, thanks, Neil. Mike, lovely talk, as ever. Look forward to lunch the week after next, something like that. There's an observation which we shouldn't overlook, which is the fact that the Pakistan Himalaya have a very different story from the main Himalayan chain. And trying to tie those two in together is obviously something which we need to work on. What I was really excited to see in your talk was the work you were doing on Nanga Parbat. And we talked about Peter Zeitler's embolism, or whatever he called it.
Aneurysm.
Pardon?
Aneurysm.
Aneurysm, that was it, yeah.
I've never understood that.
And what you said there actually makes an awful lot of sense to the kind of what we were doing a few years ago. So maybe over lunch we can discuss that in a couple of weeks' time. What I was going to say to, and this is kind of, and you've already plugged your book, which it's a fantastic read. If anyone was sitting out and saying, what can my grandchild give me for Christmas? It's Mike Searle's book. Mike and I did publish a book on Geological special publication, Himalayan Tectonics, Modern Synthesis. We edited it back end of 2019. There is a introduction in there which is got open access, so anybody can read it. So I guess you just go to the Geological website, Lara Collection, and it's volume 483, I think, and you can download the introduction, FOC. Or if you want, or Mike can send a link through to me, or to copy out to society members, because actually I think it was a really good. I take no credit for it. Mike was so pissed off with my original version. He wrote it himself and agreed to put my name on the back end of it. But it's a really good read about. There's lots of history in there and lots of ideas for Himalaya going forward. So if people are interested, then I recommend that to you.
Thanks very much, Peter. Look forward to seeing you.
Yeah, cool.
You're muted, Neil.
Sorry, I keep telling other people to unmute themselves and I forget to do it myself. Daniel, would you like to ask your follow-up question?
Yes, sorry to jump in again, but I couldn't resist it when we were talking about why India moved northwards, but why did it move so fast? The evidence that I've read suggests that it was a faster movement than we know of in any other plate movement.
Yes, that's true. And the answer is we don't really know. Well, I don't know. I don't know if somebody else knows. But that's what the evidence is. When you wind back all the marine magnetic anomaly stripes in the Indian Ocean, India moved at double the normal rates of, the Atlantic spreading, for example, is relatively slow. And India moved at more than double those rates northwards. So the Indian plate split apart from Madagascar, Antarctica, about 130 million years ago and became a sort of self-contained plate island. And the spreading sensors just pushed it north at these incredibly fast rates. And then the collision actually happened down at about equatorial latitude. So since 50 million years, India has moved northwards into Tibet by about 2,000 kilometers, possibly more. And if you look at a map of Asia, you can see the mountain belts going all the way around the western margin in Pakistan, Afghanistan, and coming all the way around Tibet, and coming down the eastern margin through the Indo-Burman ranges, all the way down to Sumatra.
Yeah, thank you for that. That was very useful as well. Are there any more questions? If there's,
Neil?
Yeah, sorry.
Sorry,
David.
I had a couple of questions, but then they ended up being comments because it was just a brilliant talk. I loved it, and I'm going to take a bit of time to look at some of it again. I wrote a question down halfway through. It said, "How does this all apply to the Caledonian orogeny in Scotland?" But you actually went straight into all that. Because I'm fascinated by all that, and I want to sort of there's two aspects. One about the low angle detachments, and maybe we're seeing some of that which we haven't recognized before. And I'm fascinated by this sort of the age range between the tight age range between the end of the orogenesis age and the sedimentation, post-orogenic sedimentation. When you're talking about less than 1 million years, we always traditionally think it was a lot longer than that, and that's fascinating that's coming out. So that was really the two comments, and I just show people my ammonite from the Kalandaki Gorge, which inspired me to look at Himalayan geology and buy Mike's book and get Mike here in the first place. So thanks to the
pleasure.
Jurassic, yeah.
Yes, that's right. Spitty shales.
Yes.
Well, no,
so
the whole.
Thank you. Yeah.
Oh well, thank you very much, David. That's really good of you. No, the comparison with the Caledonides I find absolutely intriguing because I've sort of dabbled in the Caledonides for 30 years. I did my undergraduate mapping in Erebol, and I've been leading field trips up to Assynt for about 25 years in Oxford. So I've done a big review of all of the metamorphism and magnetism all the way across from the Moyne Thrust zone down to the southern uplands. And I've come up with a Himalayan comparison that I think is kind of 80% believable. There's some things don't fit, but a lot of things fit very, very nicely. So all the highland boundary ophiolites, for example, that's all in the back thrust zone. The whole Tay Nap is equivalent to the Zanskar back thrust zone. The whole Himalayas is back thrust to the north. And then whether there's two orogenies, the Grampian and the Scandian, I think is just a matter of a gap in the geochronology. The more and more garnet dates come out, the more and more monozoite ages coming out, the two are merging together. And even when there's no metamorphic monozoite ages, for example, there's no Scandian ages, there's no Grampian ages, there's no Scandian ages in the south, there's actually a load of crustal melt granites there that Graham Oliver described years ago. So you've got to have thick crust and high temperatures in the Dalradian metamorphism at the same time as the Scandian metamorphism in the south. So my model is much, much simpler than having this flip-in subduction, which I don't like because it takes an enormous amount of problems to flip a subduction zone. You've got to flip the entire subduction convection channel. I don't like the collision with Baltica. I can't see what Baltica's got anything to do with it. Baltica has 70 million years of ultra high pressure metamorphism continually on a west dipping subduction zone. Well, that's not an Andean type collisional margin at all. So I think the entire Scotland can be, and East Greenland, which is contiguous with the Caledonides, can be explained by a very simple Laurentia Midland Valley microcontinent Avalonia collision. There's several problems, one of which is why does sedimentation in the southern uplands extend way beyond that collision? And I think the answer is probably the Midland Valley was the backstop. So it was a collision really between Laurentia and the Midland Valley, which can explain the highland boundary ophiolites, the Dalradian back thrust zone, the Grampian Scandian merging metamorphism. And one of the real keys that I've been really interested in is the newer granites, the Lake Silurian, Devonian granites, which are all very tightly constrained, 430 to 405, 410. And they're all associated with lamprifiers. They're absolutely not Andean type granites at all. They don't fit any category. They're not I types, they're not S types. If anything, they're A types. And there's something very peculiar going on in the upper mantle in the Caledonian of Scotland at that time, 430. And that's yet to be resolved by some geochemical isotopic wizzo, which is not me.
Yeah, I mean, I look at all the rocks on Island. We get Silurian labrifiers there, and with some strike slip faults, and they're all sort of, it's just weird. And I sort of said it is this thing about, well, how does the Grampian merge into the Scandian, and how far south does the Scandian type age go?
Yeah.
So it's the whole, what you've just mentioned about the Himalayas, Gibraltarian, Caledonian thing sounds like a whole talk on its own.
Sure. Yeah, I could do one on the Karakura and one on the Scotland, and one on Burma.
Brilliant. Thank you very much. Thanks very much for that. I shall study your cross sections and your. Is the paper published yet, or is it just about to be? You saying?
It's just about to be. I've just done the proof, so it should be in the next month or so.
Okay, good. Look out for that. I'll post a link to that to the Society through the newsletter.
Yes, it's great to know to see that Scotland still has quite a lot to offer geologically.
Absolutely. I might have to do a runner back to Nepal to escape the flat.
So thank you very much for that. I'd like to call on Campbell for us to provide us with the vote of thanks. Over to you, Campbell.
Thanks very much, Neil. It's a privilege, really, on behalf of the members of the Geological Society of Glasgow and our guests this evening, of whom there were many, to firstly thank yourself, Neil, as president, for handling the meeting so well, and of course David Webster, without whom none of this series of talks would be taking place at all. But in particular, Mike Searle. What a spectacular trip to the tops of the Himalayas you've taken us this evening. In Scotland, we're very used to examining the roots of mountains, but you took us right to the very top to see what we seem to have lost over a few 100 million years. Early in the talk, when you were looking at the Zanskar River Gorge, a phrase struck me, which was, "This is how you thicken the crust." And I found myself thinking of some views I've had over the last couple of years when I've been fishing in the far northwest of Scotland. And I found myself wondering, did the young Mike Searle cut his teeth, his geological teeth, on the Moyne Thrust area? And I started to convince myself that he did. It led me into an interesting little byway, and when I was fishing on a remote, very remote loch for sea trout the last couple of years, and a more spectacular setting, look at this gigantic cliff. I've climbed in there myself in the past, and it's in a mountain called Foinavan, and David has the photo that I emailed him earlier. There is the cliff.
Oh, beautiful.
And the huge cliff, Mike, you may vaguely recognize this place.
Yes, I do.
It's a cliff called Craig Urvard on a mountain called Foinavan. And the major cliff in the middle there is a whole stack of imbricate thrusts with numerous repetitions on the way up it. But quite interestingly, when I was looking at the climbing guidebook, one thing struck me. A name popped out at me, and it seemed to be a young student called Mike Searle, and I hope to heck I've got the right man here.
Yes, that's right.
But if you draw a line more or less from the very top of that cliff to pretty much down here, you will find there is a very severe rock climb pioneered in 1975 with the name Promiscuous Wall, which presumably relates to a certain amount of looseness in the rock, Mike.
That's correct.
And if we've got you, we've got the right man here. And if that is not hands-on geology, then I don't know what is. Mike, you've left us with a fascinating teaser as well about this paper that's coming out on the comparison between the Highlands of Scotland and the Himalaya. And I'm sure all of us can't wait to get our hands on that. Just like to thank you once again, most sincerely, Mike, for an absolutely fabulous evening. Thank you on behalf of all of us.
Thank you very much indeed. That's really nice to be.